In this lecture, we're going to go back to the earliest recorded mathematics, going back almost 4,000 years to both ancient Mesopotamia and ancient Egypt. In both of these civilizations, at about the same time, we get the development of quite sophisticated mathematical texts. And we're going to be looking at these texts for the origins of the ideas of algebra and also the origins of the idea of approximating values. For Mesopotamia, we're looking at what's known as the Old Babylonian period, roughly about 2000 BC to around 1600 BC. In Egypt, we're looking at the early Middle Kingdom, also over approximately the same period. What was happening in both of these civilizations, both Mesopotamia in what today is modern Iraq, and also in Egypt along the Nile River Valley, is that both of these were getting very sophisticated civilizations that had highly developed systems of commerce. They were doing a lot of construction. They needed to train a large corps of civil servants, of bureaucrats, of people who could oversee taxation, who could oversee the building projects that were coming about at that time. And these were people who needed to be trained in basic mathematical techniques. And the mathematics that we have from this period are the textbooks that would have been used in order to train these people. So it's not mathematics the way we might like to see it, which is, where did they get these ideas? How did they develop these ideas? What we get are problem books, sets of problems, together with worked out solutions. These are problems that students would have worked on and tried to emulate. Now, the problem books that we have that come to us from Egypt are really quite limited. There really are only 2 of these books, but they're both quite complete, and especially one of them. We've got the Rind Papyrus that was probably written around the 17th century BC. The name of the scribe who wrote it was Ames, and we do know that, in fact, that this was developed from or copied from a slightly earlier manuscript believed to have been written about 200 years earlier. It's quite complete. The actual papyrus roll that exists is about 13 inches high and about 18 feet long. There is one other important source for Egyptian mathematics from this period, and that's the Moscow Mathematical Papyrus that was probably written in the 19th to the 18th century BC. That exists today in the Pushkin State Museum. But unfortunately, we only have a small piece of that papyrus. Only the top edge still exists. It's about the top 3 inches of it, but the whole papyrus is about 15 feet long. So we've basically got these 2 problem books that lay out the kinds of problems that civil servants in ancient Egypt were expected to be able to do. And what is very interesting is the way that the ancient Egyptians represented number. The way we represent number today is really quite sophisticated. What we do with number is we have 10 symbols, the 10 digits, 0 through 9. And if we want to represent a number that is larger than 9, we start reusing these digits, but we put them in places that carry this extra value. So, for example, the 2 digits 1 and 3 can be combined to 13, or we can also combine the 2 digits 1 and 3 into 31. And the 3 has a very different meaning depending on whether it's 1-3 or whether it's 3-1. In the latter case, 3-1, that digit 3 represents 30. It's 3 tens. And so we take these 10 digits and we put them in different positions in order to indicate how many tens we have, or how many hundreds we have, or how many thousands we have. The system that was used in ancient Egypt is a much simpler system. And it's based on the idea, first of all, starting out by representing a number by strokes, which is certainly the very oldest way of representing a number. So 1 is a single stroke, and 2 would be 2 strokes, and 3 would be 3 strokes, and 4 would be 4 strokes. We still see some echoes of this in our modern way of representing numbers, because the digit 2, for example, is really based on 2 horizontal strokes with a curve connecting them. And the number 3 is really based on 3 horizontal strokes with curves connecting them. Now, it becomes very cumbersome if you want to represent every number by strokes. And so what the Egyptians devised was a system by which, once they got up to 10 of these strokes, they would replace 10 strokes with a single symbol, what we call a yoke. So a yoke was a single symbol that would represent 10. Once you got up to 10 of these symbols for 10, then you would replace them by a single symbol referred to as a rope. And so it's simply a spiraling symbol. That meant you've got 100. So if you wanted to represent 317, for example, you would have 3 of the rope symbols, 1 of the yoke symbols, and 7 of the stroke symbols. And if you wanted 10 of the ropes, then that was represented by a lotus symbol that represented 1,000, and so on. This was continued up into 10,000 and 100,000. In addition to that, the Egyptians were able to work with simple fractions. What they did was to think of the reciprocals of the integers. And so if you wanted to represent 1/2, you would simply take 2 strokes and draw an oval over the top of them. And so that represented the reciprocal of 2, or 1/2. 1/3 would be 3 strokes with an oval over the top of it. Now you've got a problem here in that how do you represent a number like 3/4? Well, what the Egyptians would do is represent 3/4 as a half, so 2 with an oval over it, plus 1/4, so that would be 4 with another oval over that. And that really was sufficient for the kinds of uses of fractions that you get in ancient Egypt. The kinds of problems that they would work with, one of the examples from the Rhind papyrus is that you've got a scoop and you've got a certain volume of wheat, a hekat, and the problem that was posed was it takes 3 1/3 scoops in order to equal 1 hekat. What is the size of a single scoop? And so this is one of the problems that these people who were training to be civil servants would practice. The ancient Egyptians were quite good in their work with geometry. They were able to find a lot of formulas for areas, for volumes. They knew the Pythagorean theorem. In the next lecture, I'm going to talk about Pythagoras. He lived in the 6th century BC. So the Pythagorean theorem is definitely much, much older than Pythagoras himself. In fact, it's clear that even by the year 2000 BC in Mesopotamia and in Egypt, people were very conversant with the Pythagorean theorem. They were using it in many different contexts, and so it must be much, much older than 2000 BC. And the Pythagorean theorem, the way to think about it is the way that really has been thought about throughout most of the history of mathematics. The Pythagorean theorem is really a theorem about areas. You take a right-angled triangle and you construct a square on each of the 3 sides. So you take the bottom side and construct a square on that. You take one of the other sides and construct a square on that. And you take the 3rd side and you construct a square on that. And what the Pythagorean theorem says is that the areas of the 2 smaller squares, when added together, give you precisely the area of the large square. Now, today we know the Pythagorean theorem as the square of the length of one of the legs plus the square of the length of another leg is equal to the square of the length of the hypotenuse. But what's really going on there, when we use the word square, it should be taken literally. And that's the way people have thought about this theorem right up until very recent centuries, is a theorem about areas. Another of the problems that the Egyptians solved was that of finding the area of a circle. And the problem of finding areas of things that are not square regions or rectangular regions was always simplified into the problem of finding the side of a square whose area is equal to the given area. So this is a problem that would be stated not just by the Egyptians and the Babylonians, but also by Greeks and also by medieval and Renaissance mathematicians. The problem of squaring a circle. You've got a circle of a certain diameter, and you want to find the side of a square that has the same area as that circle. And one of the amazing results that the ancient Egyptians actually were able to come up with is the way to find the side of that square is to take the diameter of the circle and take 8/9 of that diameter. So you construct a square whose side is 8/9 of the original diameter, and that actually gives you an extremely close approximation to the actual area of the circle, an approximation that is off by less than 1 part in 100, certainly accurate enough for the kind of work that these Egyptian scribes needed to be able to do. Now, the situation in the ancient Babylonian kingdom in Mesopotamia was quite different from what was going on in Egypt at that time. As I said, from Egypt, we've basically got 2 sources. From Mesopotamia, we've got literally thousands of sources, but they are not complete texts. They are tiny fragments of texts. Because in Mesopotamia, rather than writing on papyrus scrolls, what the scribes did was to record information on clay tablets. So they would take a clay tablet and they would take a reed stylus and they would stamp marks in the clay tablet. And the clay tablets generally were fairly small. And so very often a clay tablet would just contain a single problem with its solution, or perhaps it would be a table of values, but you would not be able to get a complete math text. But we have thousands of these clay tablets that have survived, and so we've got a very good idea of what was happening in Babylonian mathematics at this time. I want to focus on 2 of those tablets because they give a good indication of the kinds of mathematics that the Babylonians were able to do. The first of these is known as Plimpton 322. Today it resides at Columbia University. And it's about 3.5 inches high, about 5 inches long, and it's believed to have been created about 1800 BC. And this is a tablet that deals with the Pythagorean theorem, and in particular, it is looking at cases of the Pythagorean theorem where you can take the 3 sides of the triangle to all be integers. These are called Pythagorean triples. So this is 3 integers, such as 3, 4, 5, where 3 squared, which is 9, plus 4 squared, which is 16, 9 and 16 is 25, and 25 is a perfect square. Another example of a Pythagorean triple is 5, 12, and 13. Another example is 8, 15, and 17. And sometime back in ancient prehistory, people began, after studying the Pythagorean theorem and realizing what was going on there, to look for triples of integers that had this property. Now, what's amazing about Plimpton 322 is that it does not just find triples like 3, 4, 5, and 5, 12, 13, but among the triples that are contained on Plimpton 322 are 119, 120, and 169. If you take 119 squared plus 120 squared, that is equal to 169 squared. And it's very unlikely that anybody could find this just by chance. And if you've got any question about what's going on here, some of the other triples that occur on Plimpton 322 are 3367, and 3456, and 4825. Another triple is 4,601, if I square that. 4,800, square that and add it to the first square. I'm going to get a perfect square, exactly 6,649 squared. So there must be something going on behind this. Unfortunately for Plimpton 322, all we have is this table of values. We have no idea how it was created. And there's some fascinating mathematical detective work trying to figure out what else we can pick up from what other things we see on Babylonian mathematics to figure out how they might have come up with these triples. But clearly they must have had a general procedure for coming up with them. Now, this is a good opportunity to also talk about the way in which the Babylonians represented numbers. They started out in the same way that the Egyptians had. So they had a particular symbol, a vertical wedge, that represented 1, and 2 of these would represent 2, and 3 of them would represent 3, until they got up to 10, and then they had a new symbol for 10, and that was simply a wedge put on its side. So a sideways wedge, a horizontal wedge represented 10, and then you built up from there. But rather than going all the way to 100, the Babylonians stopped at 60. We're not exactly sure why 60, but my guess is it has something to do with the fact both that there are approximately 360 days to a year, and also the fact that 60 is a number that is divisible by many nice small integers. But they worked with 60, and then instead of coming up with a new symbol for 60, what they did was to reuse the symbol for 1. In the same way that when I'm writing 31, I reuse that 3 symbol, but in the tens place. So the Babylonians, instead of having a base 10 system based on powers of 10 as our modern numbers are, they had a base 60 system based on powers of 60. So if they would put a 1 in the 60s place, and that would then indicate that they had 60, and they could build up 60s, and once they got up to 60 60s, they would start over again with their symbol for 1 that would go into the place of 60 60s. And 60 60s is 3,600. So they would have a units place, they would have a 60s place, and they would have a 3600s place, and they could continue that. So, for example, the number 4,601, there is one 3,600 inside of that. You take out 3,600, you're left with 1,001. There are 16 60s in that. You take out the 16 60s, which is 960, and you're left with 41. So they would represent this number, 4,601, by 3,600, 16 60s, and 41 ones. The next piece of Babylonian pottery, the next mathematics that I want to talk about, is called YBC 7289. It's a rather unromantic name, but that happens to be its designation from the archaeological dig that it was discovered in. It exists today at Yale University. It probably dates from between 1800 and 1600. And what's going on this particular piece of mathematics is that the Babylonians are representing the square root of 2. We consider a square, and we look at the diagonal of the square, and the problem that they're really wrestling with is if I take the length of that square as my unit, how many times can I measure off the length of that square against the diagonal? Well, you try to measure off the length of the square against the diagonal, and you realize that it goes in once and it's not going to go in twice, so there's a piece left over. How big is that piece? And what they did then was to take their unit and break it down into 60 subunits, so 60ths of their basic unit. This idea of taking their units and breaking it down into 60ths, incidentally, is something that we still have with us today. The fact that we break an hour down into 60 minutes and a minute down into 60 seconds comes directly to us out of the Babylonian way of dealing with fractions. So the Babylonians would deal with 60ths, and if you take the piece on the diagonal that's left over, it's about 24 60ths. But not exactly. You can get 24 60ths, and then there's a little piece left over. And on this clay tablet, what the Babylonians did was take their 60ths of a unit and break it down into 60ths of 60ths. And they saw that there were about 51 of these 60ths of 60ths, but there was a little piece left over. And they then analyzed the little piece that was left over, and they found that there were about 10 60ths of 60ths of 60ths. Now, you're not going to be able to do that by actually measuring. In fact, you really can't get much beyond just 60ths of a unit. So there had to be some very sophisticated algebra that was sitting behind what the Babylonians were able to do in order to get this approximation to the square root of 2 so very accurately. The approximation that they came up with was that the square root of 2 is approximately 1 plus 24 60ths plus 51 over 60 times 60 plus 10 over 60 times 60 times 60, which in our modern decimal representation is approximately 1.414213. This is incredible accuracy. The Babylonians were able to get the square root of 2 down to an accuracy of less than 1 part in a million. Now, not only did they deal with this question of how to find approximations, there also is a lot of algebra that is contained in the old Babylonian clay tablets. It's not algebra the way we think about algebra today. And in fact, one of the big themes that we'll be following through this series of lectures is how algebra actually did develop. But it's very instructive to look at the way that the Babylonians viewed algebraic problems, because that's the way the Greeks would look at it, it's the way that the Indians would look at it, it's the way that the Chinese would look at it. It really is not up until about the year 1000 AD that we begin to get algebraic notation and algebraic ideas that really are connected to our modern way of thinking about algebra. But the kinds of problems that the Babylonians looked at were very algebraic. And one of the problems that is contained on one of the Babylonian tablets is the following. You've got a square of unknown side, and we want to add to that the length of that square, and the value is 3/4. What is the length of the square? Now, today, the way we would set that up is with an algebraic equation. We would say x squared plus x equals 3/4, and we would solve it algebraically. But the algebraic notation did not exist at this time. What the Babylonians did was to think about this problem geometrically. You've got a square. You've got a certain length that is equal to that square. Let's create a second area to add to the square. We'll create a rectangle whose height is equal to the length of the square and whose width is 1 unit, so that the area of this rectangle is exactly equal to the length of the original square. So in our modern algebraic notation, if we think of the side of the square as being x by x, then our rectangle is x high and it's 1 unit wide. And the method of proof is exactly equivalent to the way we would solve this problem algebraically today. What the scribe is told to do is to take that rectangle and break it in half. So you get 2 rectangles, each of height this unknown quantity, and each of width exactly 1/2. We take one of those rectangles and we slide it underneath our square. So now I've got my square. I've got a rectangle over here of width 1/2 and height equal to the height of the square. I've got another rectangle underneath the square whose width is equal to the length of the square and whose height is equal to 1/2. And now we complete the square. And completing the square for the ancient Babylonians, for the Greeks, again, right up until relatively recently, is filling in the missing area on an actual geometric square. So we want to fill in that little missing piece that's down in the corner. And we know exactly how big that little piece is. It's exactly half a unit high and half a unit wide. And so its area is equal to 1/2 times 1/2, which is equal to 1/4. That tells us that if I add an area equal to 1/4 to my existing area, I'm going to get an exact square. An exact square, well, I knew that the area originally was 3/4. If I add an area of 1/4, that now gives me an area of 1. And so my entire square has area 1. Well, it's easy to determine what the side of that square is. It must be a square of side 1. But I know that the side is also equal to the unknown side of the original square plus 1/2. And that tells me that the original square must have been half a unit by half a unit. Now that's exactly what we do algebraically today. And this is one of the reasons in the first lecture why I talked about the power of looking at the history of mathematics, because teaching students how to solve a quadratic equation by completing the square suddenly makes a lot more sense if you're actually able to think about it geometrically and not think about completing the square as some abstract operation, but actually as taking a geometric square and filling in the missing piece. And once you understand what's going on geometrically here, you can then take that idea and see how to encode it in the algebraic notation. But it would take 3,000 years before these problems of solving quadratic equations got encoded in the kind of algebraic notation that we are familiar with today. I've been looking at Babylonian mathematics and Egyptian mathematics basically in the period 2000 to 1600. I've been looking at the kinds of texts that were being used to train the scribes, to train the civil administrators. You do not get a lot of mathematics. You get some mathematics after 1600 BC, but the sources are not nearly as rich as they had been before, and to some extent, much of the mathematics goes underground at this point. Much of the mathematics in Babylon and Egypt is taken over by the priestly castes, who are using mathematics for astronomical observations. I'm going to wait until Lecture 5 before I really begin to look at astronomy and its effect on mathematics in any detail. But one of the things that's important to remember is that the mathematical tradition continues both in Mesopotamia and Egypt. We have every reason to believe that it becomes much deeper and richer, largely because we know that it has direct influence on what would come into being in the Greek world starting in about the year 600 BC. But it does become secret knowledge. This ability to understand what was going on in the heavens was understood as a way of predicting what was likely to happen on Earth. After all, the position of the sun in the heavens certainly has great influence on what's going on the Earth. And so very likely the position of the planets, the position of the moon, should also have an influence on what's going on. And this then would become secret knowledge. In Mesopotamia, these mathematicians, astronomers, astrologers would come to be called magi. And the magi who visit the infant Jesus in the Christmas story are mathematicians, Persian mathematicians from Mesopotamia, who have seen a star and have realized the astrological implications of the star that they saw and follow it. And so we get mathematicians appearing in the New Testament. In the next lecture, we're going to jump ahead 1,200 years to about 600 BC. And we're going to see how the Greek mathematicians of that time picked up the ideas that they inherited from Mesopotamia and from Egypt, and then developed that mathematics in very new and very important directions.